Thank you for watching this presentation. I'm Daiki Takeuchi at NTT Corporation. I'd like to talk about pre-processing and post-processing method for audio captioning. This is an outline of this presentation. Let's start my presentation with research background. Automated audio captioning is cross-modal translation task. Input audio is translated into a description of the audio using natural language. This task is set up at DCASE 2020 Challenge Task 6. Then, we address 3 research questions. Our research questions are how to augment the limited data for effective training, how to decide the best description for given audio, and whether post-processing such as beam search decoding is effective in automated audio captioning. First question is based on the rule of task 6. In this task, we cannot use external data including pre-trained model. So, we only use the provided dataset. This is one example of the provided dataset. The provided dataset has audio file, 5 captions, and meta information including file name and keyword. Thus, it should be considered to train efficiently with some data augmentation method. Second question is captioning specific problem. Audio captioning has 2 indeterminacy problems. One is word selection, and the other is sentence length. In audio captioning, we describe one acoustic event or scene in several different ways using different set of words. Also, one scene can be expressed by brief or detailed expression. Since this indeterminacy leads to a combinatorial explosion of possible answers, these problems should be resolved by any method. In the third question, we consider post-processing method used in other text generation tasks are also effective for audio captioning or not. It is expected that obviously incorrect output is discarded by post-processing. Next, I talk about the proposed method based on our research questions. This is an overview of the proposed method. The proposed method is broadly divided into 3 elements. Each of element corresponds to each of the previously mentioned research questions. DNN architecture is based on sequence-to-sequence model. We used bidirectional LSTM and LSTM for the encoder and decoder respectively. First, we will explain about data augmentation element. This element has 3 modules consisting of mix-up, TF-IDF-based word replacement, and IDF-based sample selection. Mix-up is data augmentation method that has been validated effective in past DCASE challenge tasks. In the proposed method, audio data is mixed in logmail filterbank domain. Since text is input as a set of class labels, direct mixing is not suitable. Thus, the embedded word tokens are mixed. TF-IDF-based word replacement randomly replaces words with raw TF-IDF score. The TF-IDF score of each word is calculated before training. In training phase, words with raw TF-IDF score replaced based on it. For example, red words below sentence has raw TF-IDF score because they are used any sentence. Then, these words are replaced with other raw TF-IDF words. By replacement these words, we expect that training more focuses on words with high TF-IDF score. TF-IDF-based sample selection aims to avoid overfitting for high-frequent topic. Here, we assume that infrequent acoustic event or scene contain infrequent words or idioms in the dataset. Then, by calculating the average IDF of each data and regarding it as the distribution of sampling, the sampling frequency of infrequent acoustic event or scenes is increased. Next, I talk about multitask running. We use multitask running method, meta keyword estimation, caption keyword estimation, and sentence length estimation. To solve the indeterminacy of word selection, we use two keyword estimation methods. Keyword dictionary is made from meta information of the dataset. The meta and caption keywords are extracted from keyword dictionary before training. Then, two keywords estimated from audio. Two keyword estimations are treated as multi-level classification problems. Furthermore, the estimated meta keyword is embedded again and passed to the decoder. To solve the indeterminacy of sentence length, we use sentence length estimation method. The number of each caption is counted before training and estimated from audio by the encoder. Sentence length estimation is treated as classification problem. After that, sentence length probability is passed to the decoder to utilize estimated information in decoding phase. Third element is post-processing. As a post-processing, we apply beam search decoding and test time augmentation. These are only used in test phase. Beam search decoding can discard obviously incorrect output candidate, and it is effective for other text generation tasks. Thus, it is expected to be effective for audio captioning too. In the proposed method, beam size is set to 5 and n-gram blocking size is set to 2. By bigram blocking, a hypothesis in the beam is discarded if a bigram appears more than once within it. Test time augmentation is used for decreasing bad influence of data cropping. In the training phase, the audio input is randomly cropped to limit the length of time. Thus, in the test phase, we also randomly cropped and zeroed the audio input. When the data is cropped, the uncropped parts are not used for inference. If the uncropped parts has important information, an incorrect result may be output. So, the effect of cropping is mitigated by cropping multiple times with one inference and averaging the output of each. As explained so far, the proposed method has 8 modules to improve the accuracy of audio captioning. To solve our research questions, the proposed method has 3 data augmentation, 3 multitask running, and 2 post-processing modules. And our method yields the best score at DCASE 2020 Challenge Task 6. On the other hand, it is not clear which modules are more effective for improvement accuracy of audio captioning. In this presentation, we also conducted detailed experiment to confirm which elements or modules are effective. To investigate the effect of each modules, we conducted 2 experiments. First one is element-wise aberration study, and second one is module-wise aberration study in effective elements. In the experiment 1, the proposed method aberrated each element is used. Data augmentation, multitask running, or post-processing is removed from the proposed method. This is the results of experiment 1. From the score of spider, data augmentation and post-processing are effective in the proposed method. The score is decreased 1.8 from the proposed method when these elements are removed. Especially, the proposed method removed post-processing decrease BRU3, BRU4, and CIDR significantly. Since beam search decoding modify output to be appropriate as a sentence, the score based on trigram and tetragram are affected. On the other hand, multitask running is not effective in this case. This is an example of the output. Audio data is like this. And below sentences are the ground truth and the output of the proposed method. When the data augmentation element is removed, the output has incorrect words because training may not be efficient. In the proposed method without post-processing element, there is obviously incorrect word sequence. That incorrect word sequence can be modified by post-processing such as beam search decoding. In addition, while a ground truth caption describes that this is the sound of the toilet, the outputs of the proposed method did not contain the words which indicate the toilet. Thus, it is difficult for the proposed method to describe a complex concept like this. In the experiment 2, one red module is removed from the proposed method. For example, we only removed mix-up module from the proposed method. This is the results of experiment 2. In data augmentation element, mix-up is more effective. On the other hand, word replacement is not effective. So it is need to use paraphrase generation or thesaurus-based word placement for effective text data augmentation. Since there is little difference of audio scene distribution between training and test, sample selection may be not effective. In post-processing element, beam search decoding is effective like other text generation tasks. In particular, BRU3, BRU4, and CIDR are decreased significantly, same as the experiment 1. The reason why test time augmentation is not effective may be crop size is almost the same as the size of audio data. Let me summarize this presentation. We propose automated audio captioning method with 3 data augmentation, 3 multitask running, and 2 post-processing methods. And it is confirmed that mix-up and beam search decoding is effective for improving accuracy of automated audio captioning. As the future works, we investigate how to apply external data such as pre-trained model and other domain or modal dataset. Thank you for watching this presentation. I'm looking forward to discuss in Q&A session.